Hello, my name is Todd Hayes, and this is my Physics 2 Lab 5. Happy last lab, everybody. So we dropped a magnet through a tube of aluminum foil this time, looking at Faraday's law. We saw a braking force, or we saw the equivalent force generated due to the change in flux inducing a magnetic field reacting then on that magnet again. And we also calculated through a simulation the magnetic field that was actually generated, the current that was induced in the conductive tube as a model of rings, and we also looked at the braking force that was exerted on the falling magnet and compared the real world results to those of the model. So I broke my magnet. This is the same magnet from Lab 3 that I accidentally shattered, and I didn't want to buy another one, so I didn't. So I used a broken magnet. I taped it together. I think it affected more in this lab, uh, but hypothetically it shouldn't prevent anything from being too accurate. But I think that actually did end up mattering in this lab a little bit more than the previous one. So as far as what actually happened in the code, um, as far as the geometry of the tube, it was about a foot long for about a third of a meter. There was about 8 millimeters of thickness of wall of actual aluminum. And then there was quite a large distance before that actually started. As far as the magnet, it's still 40 grams, and it's the calculated dipole moment from Lab 3 is still 5.64. And then also, these next two sections are just translating these formulas over into GlowScript. With the first one being the calculating the field in space from a magnetic dipole given the dipole moment and the radius. The next is calculating the magnetic flux with respect to time. Um, and then it's also this also bakes in a little bit of the calculation of the actual how the flux is actually happening or how the flux is actually changing. Sorry. Um, and then also how things are actually using to take all of that and apply it to figure out the force on the ring. So actually applying this, the time it took for the magnet to fall through the tube based on my actual experiment was about less than half a second. And as you see in the model, it says it was allegedly took 3 seconds, which is not what happened, due to a variety of factors. Most of which being perfect positioning, the orientation, the vacuum, the fact that there wasn't necessarily as much of a there actually wasn't the air in the way for air resistance. Sorry, and also the magnet couldn't tilt off kilter to be able to affect any of that. So there were lots of things that made that go wrong. But also thinking about as far as the applications of this experiment and the extension questions, aluminum is not as good of a conductor as copper, and so if we think about what if the resistivity of all the conductor we used in this experiment was as close as possible to zero, that magnet would either slow down completely or stop because whatever force is being pushed down has a perfectly proportional amount of current being induced if there's no resistance at all. And so the magnet would slow to either a halt or very, 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 very slowly. Um, Additionally, if there were holes or slots cut in the tube, we thinking of that ring model, if we're bringing them down into infinitesimally small rings, there's less rings for current to flow through, and so there's less flux overall across the entire tube. And so as the magnet passes through these areas, the magnetic braking force is less, and so it would actually speed up and take less time to be able to fall all the way through. Um, Overall, this lab was very, very straightforward in terms of the execution and then turning that into a model. However, we saw that due to a lot of factors that I thought that I had controlled, that I apparently did not actually control, the time that it showed it taking was significantly longer than what it took um, experimentally. Thank you so much, and enjoy the rest of your semester, and good luck on all of your finals.